Hello and welcome to today's video. Today we are going to implement an algorithm to generate all prime numbers less than or equal to a given number. By definition, a prime number is a number that is divisible only by itself and 1. For today's exercise, I have created an empty starter project and we will be building it out to the final version. Links will be available in the description section of this video. So let's get started. The approach used in today's video is based on the Sieve of Eratosthenes. Eratosthenes was a Greek mathematician from the 3rd century. So let's say we'd like to generate prime numbers less than or equal to 20. But we'd like to generate this for a given value of n. So for that, we'll build out the algorithm. Before we jump into the code, I'd like to walk you through the steps so that we can visualize how the algorithm will work. We first create an array of Boolean values where the index represents the number we'd like to check whether it is prime or not, and the value of this array element will be true if the index is a prime number and is false if the index is a non-prime number. We start the array from 0 and go all the way up to 20, which means that we'll need an array to be of size 21 because we are including 0 to 20. So here's my array which goes from 0 to 20. Initially, we mark the value at index 0 and 1 as false because we know that 0 and 1 are non-prime. We mark the rest of the values in the array as true. Now for this example, I'm going to write F for false and T to mean true. So as you can see, the first two values are false and the rest are all marked as true. We will then use the Sieve of Eratosthenes to mark the value of non-prime indices to be false. The way this works is we start with the next index with the value of true, which means that it is a prime number, and we mark all its multiples as non-prime, that is, we mark them as false. So in our case, the next prime number in our array, or the next value which is true, is at the index 2. So what we need to do is mark all the multiples of 2 to be false. So as you can see, because 4 is a multiple of 2, I have marked it as a non-prime indicated by false. Same goes for 6, 8, 10, so on and so forth. Now we move on to the next prime number, which is 3, and mark all the multiples of 3 to be non-prime. Here you can see I have marked 15 as well, which was previously marked as prime, as a non-prime value. So we continue in this manner with the next prime, which is 5. So as you can see, if we continue in this manner, we can get the list of prime numbers from this array. So the next prime number is 7, and we can see that its multiple, that is 14, is already been marked as non-prime. If we go to the next prime number, that is 11, we can see that the array doesn't contain any more than 20, and therefore we can actually stop the looping till half the array size, that is from 0 till n by 2. Now let's jump into the code and implement this solution. So here I've got IntelliJ open, and the first thing I'm going to do is create a package. I've created a class called prime number generator, and in this class I'm going to add a method which lets us generate prime numbers up to a given number. I'm going to return an empty array so that I can start writing the test and then we can implement the functionality. I defined a field in this test of the type prime number generator. I'm going to initialize it in the before each annotated method. Since 2 is the smallest prime number we can have, I'm going to add a condition to throw an error if n is less than 2. As you can see, the test is failing because it is expecting the code to throw an exception. So let's fix the code to make this test pass. Great, the test passes. Go back into the test and add the test to actually verify that we are able to generate the prime numbers we want. So as expected, we are returning an empty array and hence the test is failing. Let's go back into the prime number generator and implement our functionality. So firstly, I'm going to define the array which will tell us if a number is prime or not at the given index. By default in Java, an array of booleans contains false values. So we don't have to set the values for the index 0 and 1 to false explicitly because we know that they are not prime anyways. The next thing we need to do is we need to set the values from 2 up till the end to true. So in this step, what I've done is simply set the value for each element starting from 2 all up the way till n to true. Now we will look through this array and for every prime number we will mark all their multiples as non-prime. So firstly we check if the value at this index, that is if this number is a prime. If it is prime, then we mark the indexes which are multiples of this index to be non-prime. For example, if I is 2, then we want to start marking 4 as non-prime. Then we go to 6 and mark it as non-prime and so on and so forth. Once we mark the first multiple as non-prime, we then need to move to the next multiple of I. And this loop will continue till all the multiples of the index I have been marked as non-prime. Now we want to be able to define an array of values which are prime numbers. And how do we get that? So essentially, the isPrime array now contains true for all the prime numbers and false for all the non-prime numbers. And the index at which the value is true, that index itself is the prime number we want. So let's firstly calculate the number of prime numbers in the East prime array. And we filter out only those elements which have a value of true, and we simply count them. Now that we know how many elements are actually prime, we can create an array of that size. Then need to store the indices from the East prime array for which the value is true. You'll notice that I've created two variables, I and j. The variable I is an index into the East primes array, and the variable j is an index into the primes array. Let me show you how that works. So what I've done here is, if the value at the index I in the East prime array is true, that means we have identified that I is a prime number, then we simply store the value I into the primes array. So we keep on doing this till we have finished looping through the East prime array. And finally, we can simply return the primes array. If we go back to our test and we run our test again, we can see that we have successfully generated the correct prime values. We'll finally run all the tests to make sure that there is no problem due to the new code added. And as you can see, everything looks good. Now if we go back into the prime number generator, there is some optimization we can still do in this. If you look at this for loop closely, we'll notice that we don't need to iterate till the entire length of the array. So if I go back to the example, you'll see that once I had reached around halfway mark, there was no prime numbers left to be detected. So let's modify our code to add this optimization. We'll simply divide this by 2, and I do not want to calculate this every time, so I'll extract this into a variable. Let's just call it bound, and our check will go all the way up till the bound. So let's run the test again and verify that we've not broken anything. Okay, that looks good. Now if you notice, the value 20 is an even number. I will add a test to verify that we can generate prime numbers correctly up till an odd number. So in this test, I'm passing n equals 37. I'm expecting the prime numbers to be generated here. And that looks fine as well. So that means that we can generate values up to not only even but up till odd numbers, and even if the last number is a prime number, our algorithm works as expected. So that's it, guys. Thank you very much for tuning in. If you like this content and you'd like to see more of it, please consider subscribing and liking my videos. Thank you.